Hello and welcome to the Daily Space for today, Tuesday, January 5th, 2021. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brains. And our top story is one that may hurt. There are a lot of times when I read theory papers and think, that's a lot of math and nothing I can test with a telescope. Going into this next story, I was fully prepared to discard it as something completely untestable. But it turns out a team of theorists have figured out how we may be able to detect tiny black holes left over from the universe's formation. For roughly the first 400,000 years of our universe, everything was more or less a hot soup of stuff like atomic nuclei, free electrons, and light that was constantly interacting as our small universe expanded and cooled. Then one day, it cooled enough that the electrons and atomic nuclei could come together as neutral matter, and the light could fly away as the cosmic microwave background. That neutral stuff, it became stars and galaxies through gravitational collapse. Now, this wasn't a completely smooth distribution of material. And places where there is a bit more stuff than the surroundings, that's where galaxies started. But according to some theories, there were rare spots that contained 50% more material than their surroundings. And those really much denser than their surroundings places, those places collapsed down, in theory, into tiny black holes, objects the mass of the moon, with an event horizon the size of a grain of sand. Now, if Stephen Hawking's was correct and black holes evaporate, then all these tiny black holes should have puffed out of existence billions and billions of years ago. If they didn't, however, they could still be out there floating among the stars. Now, detecting a grain of sand in the vastness of space seems like it should be an impossible feat, but a remarkable instrument on the 8.2-meter Subaru telescope in Hawaii may be able to do it. The Hyper Super Prime Cam has a massive field of view that is so high resolution that it can observe 100 million stars in the Andromeda Galaxy simultaneously. And it can do it fast, taking new images every few minutes. Theorists at the Cavalli Institute for Physics and Mathematics of the Universe in Japan believe that if there are primordial black holes out there, they should periodically pass in front of these stars and change how we see their light. Mass can act like a lens, bending light, and like a magnifying glass focusing sunlight on a blade of grass. Mass can make distant things appear brighter if you're in just the right place. Now, if a primordial black hole passes exactly between us and one of those 100 million stars, we will be in that right place and we will see that star get brighter and fainter in a special way that is unique to these gravitational lenses. And they may have already seen one. These researchers using Hypersuprime may have seen one. In a new paper in Physical Review Letters, the team discusses an event that occurred during the first set of observations that is consistent with one of these moon-massed, grain of sand sized primordial black holes. It could have been a fluke. But if more of these detections are made and they are consistent with the population of primordial black holes, well, these folks will likely get a Nobel Prize and we'll have a new and intriguing candidate for dark matter. And there are also new possibilities for multiple universes existing. But that is a story for another day and another show. Expect to see all of this covered on Astronomy Cast at some point in the not too distant future. But for now, we're going to take a break. And when we're back, we're going to continue our explorations of the early universe.
Welcome back to the early universe. A team of astronomers using the Very Long Baseline Array observed galaxy PSO J0309 plus 27 and captured previously unseen detail in the jet of material being ejected. This galaxy is what is known as a blazar, which is an active galaxy whose jets are pointed in the direction of our solar system. This blazar happens to be the brightest radio emitting one seen at such a distance, 12.8 billion light years away. At that point in time, our universe was less than a billion years old. The brightest part of the radio transmission is at the bottom right of the image, where the galaxy's core is located. The jet then extends up to the left from the core, propelled by the supermassive black hole's gravitational energy. The jet becomes thinner and less bright as seen in the image, and the entire length is about 1600 light years. Incredibly, you can even see some structure within the jet. The galaxy and its jet were observed by the team in April and May of last year, and the observations may help us understand the rarity of blazars in the early universe. The full paper may be found in Astronomy and Astrophysics.
As much as we've so far been able to learn about how our early universe evolved, we still aren't really sure how long the process took. Currently, there are two camps: those that look at the cosmic microwave background, seen on the left, and put the universe at 13.8 billion years, with a nice slow expansion of 67 kilometers per second per megaparsec. That means that every megaparsec of our universe gets 67 kilometers bigger every second. Now, there are also those that look at supernovae and gravitationally lensed distant quasars and get an expansion of a zippy 74 kilometers per second per megaparsec. And if the universe is expanding faster, that means it took less time to get to the state it's currently in, and it's younger. Now, since these two sets of scientists look at different light, with one camp looking at the first light of the universe and the other looking at light from the past 11 billion years, it's entirely possible that there is some physics that happens that we just don't know that causes this discrepancy between the two sets of measurements. But since no one wants to be wrong, we are seeing teams putting out new measurements and saying, no, we're right. And you're going to see this in the news a lot right now because there is a team at the Atacama Cosmology Telescope that has confirmed the Planck satellite's measurements of the cosmic microwave background. And since they both looked at the cosmic microwave background, both Planck and the Atacama Cosmology Telescope, it's not entirely surprising that they got the same results. This work was led by Steve Choi and appears in the Journal of Cosmology and Astroparticle Physics. We also have news that there are astronomers looking at gravitational wave data and realizing that their data has enough inconsistencies from one object to the next that their measurements of the expansion of the universe is consistent within errors with both groups. This work appears in Physical Review Letters and is led by Xianyu Chen. Meanwhile, the supernova and gravitational lens groups are consistent with each other and plugging away to demonstrate their accuracy even more. Bottom line, you're about to see a bunch of news saying we know how old the universe works, but we don't know how old the universe is. And if anyone says they know how old the universe is, ask them to explain both sets of data from the first light and from more recent light. And if they can't explain both sets, they don't actually know how old the universe is. Does your head hurt yet? Mine does. Let's take a break. When we come back, we're going to bring it all back down to Earth, or rather Mars, as we look at amazing new data about the red planet. Mars is an exceedingly complex world, and understanding what forces have shaped its surface requires detailed image data. The Mars Reconnaissance Orbiter spent over a dozen years imaging Mars at 5 meters per pixel. And in 2018, the Murray Lab released their first nearly global mosaic of these seemingly countless images. The images came from the Mars Reconnaissance Orbiter's context camera. And when combined into a single 8 trillion pixel map, these images make it possible to trace out river features, lava flows, and more. Now, roughly 2 years later, this mosaic has produced the first global study of riverways and deltas on Mars. Published in the journal Geology, this work, led by J.L. Dickinson, traces riverways from their source through to their depositional ridges. Now, we're all used to seeing the valleys carved by rivers as they flow across the landscape. What we so often forget about is that all that removed rock had to end up somewhere. Here on Earth, we can see ridges left where dried out rivers ended. The most spectacular are in deserts like Death Valley in California and in Chile's Atacama Desert. Today, all of Mars is either a desert or ice. And this means that it's easy to find these depositional ridges with this data. Scientists had previously been able to locate some ridges in regional data. But with this global mosaic, 18 new ridges running as much as 100 kilometers long were found. These ridges are large, each with a width greater than 70 meters or more than half of a football field. And they demonstrate that Mars once had great rivers. Unfortunately, that once was long ago. Martian rivers appear to have run 3 to 4 billion years ago and then dried completely as the Martian atmosphere escaped into space. Mars is a changing world in every way.
One of the ways in which Mars changes is similar to one of the ways the Earth changes. Mars's axis wobbles. Known as the Chandler wobble, these tiny shifts or wiggles change where the axis of a planet points when the planet isn't a perfect sphere. Now, we know Earth is an oblate spheroid, meaning that our planet bulges around the equator due to the Earth's rotation. And the wobble is similar in effect to how a top sways as it loses speed during its spin. In the case of Earth, that wobble is about 3 to 6 meters. On Mars, it's only about 10 centimeters. These new measurements are the results of almost 2 decades worth of data collection on gravitational effects by NASA's Mars Odyssey and Mars Reconnaissance Orbiter. Per the article, the large quantity of data collected over 18 years and not available during earlier analyses ensured that the identified wobble was intrinsic to the planet's shape and interior rather than outside factors like seasonal melting of polar ice caps. So, why doesn't the Earth's wobble slow down with the wobble like a top? The motion should dampen, but instead it persists due to the fluctuations in our ocean bottom and atmospheric pressure. We don't yet understand why the wobble persists on Mars, but this newfound Chandler wobble may provide us insight into the interior of the red planet, particularly how the mantle deforms over longer periods of time, since the motion is driven by properties of that mantle. The full paper can be found in Geophysical Research Letters.
Speaking of planetary tilt, the northern hemisphere is finally getting longer days. And as bad as our winter may seem, I'd like to let you know it could be worse. It turns out the Northern Hemisphere has an ever so slightly less frigid winter thanks to a trick of geometry. Each year at the beginning of January, Earth has its closest approach to the sun, bringing us just that tiny extra bit closer. This year, the closest approach, or perihelion, occurred on January 2nd. Now we are on the retreat from the sun, But since there is only a small difference between our closest and furthest distance from the sun, the tilt of the planet is, well, the thing setting our seasonal thermometer. When we come back, we're going to be talking about weird radio signals that probably aren't aliens, but are still worth observing.
Right before I went on vacation and we took our winter hiatus, news leaked that the Breakthrough Listen project had found their first candidate signal in their search for extraterrestrial life. The headlines went a little wild, and of course, my other job dealt with a bit of the fallout. Keep in mind that we're covering this story because it's newsworthy, but the papers aren't published yet. The signal was found in archival data from 2019 and came from radio emissions from basically Proxima Centauri, only 4.2 light years away. The expectation, because scientists aren't optimistic on this front, is that we will find a somewhat terrestrial source for the signal. But that hasn't been found yet. Andrew Simeon, Breakthrough Listen's principal investigator, told Scientific American it has some particular properties that caused it to pass many of our checks, and we cannot explain it yet. The signal was found in data from the Parkes Observatory in Australia while the telescope was studying Proxima Centauri. It's a narrow beam signal around 982 megahertz, which is narrower than what we usually observe from human made satellites and spacecraft. There is also an intriguing drift to the signal, and that mimics what we see when planets are in motion and giving off their own signals. However, the signal could be coming from a traveling spacecraft of our own design. As Seth Shostak of the SETI Institute wrote, with the large volume of space technology orbiting the Earth and beyond, it can be extremely challenging to pinpoint which signals may be non human made. The signal needs to be reobserved before any conclusions can be made, so it's still not aliens. But it's not aliens. Finally, we bring you a fascinating little bit of astronomy history. Have you ever looked up at the Pleiades or seen pictures? The asterism is also called the Seven Sisters. So, why do we only see six stars? In Greek mythology, the Seven Sisters were daughters of Atlas, who was being punished by Zeus for, well, being a Titan, and Atlas had to hold up the sky. To protect the daughters from the evil machinations of Orion the Hunter, Zeus transformed them into stars, but one ran away to be with a mortal, hence six stars. There's a similar story found in Australia among Aboriginal groups. Still young women, important in women's ceremonies and stories, still being hunted by their version of the Orion constellation. There are variations in why the seventh sister is missing, but there is always an explanation. How do two disparate cultures have such similar explanations for an astronomical story? It turns out that this story reappears in culture after culture, and astronomers and anthropologists alike wanted to understand why. Modern humans descend from people who lived in Africa, and the story possibly migrated from there outward early on and changed with the retelling while keeping the major elements the same. That's the anthropological explanation. The astronomical explanation is that 100,000 years ago, when humanity was still in Africa, the stars Pleione and Atlas were actually separate to the naked eye, but everything moves, and now they look like one star. The data for this explanation came from measurements done with the Gaia Space Telescope, and I personally think it's a fascinating story all around. This has been the Daily Space.
Thank you, everyone, for dealing with our first new episode on television. We are so proud to be on Houston Channel 21 with Now Media. Today's episode was written by myself, Dr. Pamela Gay, and by my co-host, Beth Johnson. Engineering will be provided by Ali Pelfrey and web content produced by Beth Johnson.
You can get a complete transcript, show notes, and see images related to each of our stories at our website, dailyspace.org.
We are a production of the Planetary Science Institute, 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks to the generous contributions of people like you.
To learn more and to donate today, please visit our website, cosmoquest.org.
We made it through, Beth. We made it through.
Yay!